Okay, so we're going to explore the P-Basic command called freak out. So chic. And so if you'll take a look at the screen here, we have a very simple program. And it will just have a do loop, so it'll continually do this. It'll issue the freak out command using output pin number 4. The duration of the freaking out will be 10,000 milliseconds, which is 10 seconds, of course. And the frequency of the sine wave in hertz, we're just going to do one sine wave, is 261 hertz. I think that might be close to a middle C. I'm not sure. So, that being said, let's bring up our document camera. And take a look at what we have here. Okay. As you can see, we have a basic stamp. And the basic stamp has an output pin, pin number 4, is going to scope probe for channel 1. It's also going through a resistor to a capacitor to ground, and then through another resistor to another capacitor to ground, and that's where we're taking our output. So let's back up a little bit and let's take a look at, I'm going to go over to our program again. Let's take a look at what the basic things we're doing are. Remember, in this case, we are using pulse width modulation, PWM, to affect something. PWM uses a digital signal. It's either totally on or totally off. But by varying the amount of time that the signal is totally on or totally off, and filtering that, removing those high frequency, fast moving edges, and just sort of letting the pulse width modulation signal average out, if you will, we can get something closer to an analog output from a microcontroller that can only do digital outputs. The basic stamp can only do digital outputs. So that's one of the ways we can make a sort of digital to analog conversion. And so what's done here, here's the freak out command with all the, the pin, the duration, the first frequency, and you can even have a second sine wave at the same time if you'd like. So this circuit right here, I think we can actually zoom in a little bit on this. This circuit right here is a low-pass filter. Remember that capacitors do not like changes in voltage. They resist changes in voltage. So that being the case, as the pin goes and does its pulse width modulated thing, this circuit with an RC and then another RC is going to form a low pass filter. That is, slower changes will be allowed through, but fast changes will not. They'll be absorbed by these capacitors, these charge buckets here, and we'll get a signal that comes from there. So right now we are issuing the freak out command, and I'm going to move the document camera so that you can see the oscilloscope screen, and that doesn't show up very well, does it? Let's see what happens if we try to do something like that. And maybe we take the, whoa, maybe at the same time I can take the colors down a little bit here, take the brightness down. Now let's see if we can get something that comes closer to focusing on this screen. I guess that's about the best I'm going to get for now. Well, the bottom trace here, this is the microcontroller output pin, and if I were to slow this, I should say speed this up, and as I look at some of these places, like right now I'm looking at a voltage that is very close to the midpoint of the microcontroller output, between the duty cycle of the pulses. They're high about the same amount of time they're low. And if we stop this for a second, you can get an idea here. Let's see. So here's about a half a cycle. And if I zoom in on it, you can see the pulses are high about as much time as they're low. So, and that gives us a channel 2 voltage. It says about 2.75 volts here. We're hoping for 2.5, but you can see it's pretty close to the mid-range. And if we were to dial this thing way, way, way over here, let's see. You can see the pulses are beginning to get fatter now. Now, even though they look smaller, I changed the time base, but you can see the pulses are getting fatter, and the voltage on channel 2 here is rising, because the low-pass filter is kind of integrating up, taking the average of those things. The average of something that's low for a short time and high for a long time is going to be closer to the high voltage. And so this takes us up here. You can see the pulses are very wide, and they're only low for a brief time compared to how long they're high. And that's the thing at its height. If I keep going over here, we go through the mid-range where they're about equal. If I go all the way down to the end, now you can see I'm down to ground here. You can see that has a ground symbol on it, hopefully. And the pulses are low almost all the time. So it's kind of cool here, I think, anyway. By the way, these pulses, they look like they get higher here and lower, but it's just an artifact of the way the screen shows the pulses combining together. These pulses, as you saw when I turned this way down, you see they don't go high and low that much. They're really about the same level. I think it's more an indication on the screen to show you that they're crowded together more. That's kind of an optical illusion. So there you go. And now if you want to hear this thing, let me go back and brighten this up a little bit. If you want to hear this thing, I've got a computer speaker over here, and right now, let's remember what our our output was near a middle C. So if I take this thing and I connect it, hopefully you can hear that. That's near a middle C. And if we want to change it, we could go up an octave. By going up an octave, we just make the sine wave cycle through twice as many times per second. So 261 double would be 522. And we'll load that code in. And if I showed you the scope, you'd see that there are more sine waves on the scope now because the signal's going faster. And that's a little higher. And we could go to we could double that if we wanted to and go to 1044. And go up there. Now, if we want a couple of sine waves at the same time, we actually can do this. We could try something like, let's try our 261 and a 522 at the same time and see what that sounds like. Here it is on the scope, by the way. The two sine waves combine on the scope in and give you this sort of, waveform here. Well, let's see what they sound like. Well, they're an octave apart, so I guess it didn't give us that much difference. Let's pick some notes that are different. So let's say we can look up a couple musical notes here. Frequencies of musical notes. And of course the A is, in the United States, the standard A is 440 hertz. In Europe it's 432. So let's look at this. C4 is middle C, that's 261. 261.63 hertz. And let's say take a C and an E, which would be a musical 1, 2.5 steps. So let's take an F, a C and an F. And so we need 261, close to 262 really, and a 349. So let's go back over here and make this closer to 262 and a 349 and see if we get something that sounds like a chord out of that. And that's running now. Hear that? Almost sounds like dial tone, right? That was a chord. Let's go back. So how about a musical? That was a musical fourth, right? We went up 1, 2, a half, and so 2.5 whole steps, or 5 half steps. That's a musical fourth, and the fifth would be G4 here at 392. So let's try it with G at 392. And we'll load that. Okay, so there's two different notes at the same time. And there's also a command called Dtmf Out, dual tone multi-frequency. That's what that's what touch tone telephones used when people were using landlines and that sort of thing, and they still exist. So let's take a look at Dtmf Out. And we see that it's there somewhere. So I guess we have to go back to the beginning of our manual, or toward the beginning. We've seen PWM. We've actually run that and done it. There's Freak Out. And here's Dtmf Out. They show a telephone line interface so that you could actually dial on a standard phone line. Do be careful of that. Okay. So Dtmf Out, if we look at one of these commands, let's zoom in here. And so we have a variable that is a digit to dial, and that digit I don't know. There's too much fooling around, but you get the idea that they can, if Freak Out can make two sine waves, dual tone multi-frequency. Well, multi-frequency signaling on the telephone network was what got our the illustrious and somewhat perverted Captain Crunch back in the phone freaking days. He could whistle into a phone, and I believe he got the name Captain Crunch because at one time there was a whistle in the Captain Crunch cereal that was exactly, was it 2100 or 2600 hertz, and that would key in the long distance signaling. And before, this was even before touch tone, which is called DTMF, or dual tone multi-frequency. With MF, the machines between cities and everything could signal right over the phone line with some tones to send information so that calls could be forwarded, across the country or wherever. Dual tone multi-frequency works on the idea that there are actually 4 frequencies for the columns on a keyboard. Even though we typically on a phone would only see 3 columns, there's actually a 4th one defined. So there's 4 frequencies for columns, and there are 4 frequencies for rows. And the column frequencies are in one group and the row frequencies are in another. And whenever you push down a button, there was a transistor oscillator there that, based on the resistors and capacitors and pot core inductor on the back of that dial, would oscillate at 2 different frequencies and send that tone up the line. The central office would then see your digits and say, oh, I see what number you're dialing, and connect you. So Dtmf Out is the same as touch tone, and it's 2 frequencies at once. We've seen Freak Out do that, and I just don't feel like degaussing this program here. And you can see they have various phone numbers here, and they have some things that one has to figure out. There's our exact same circuit. So I guess what we do is the following DTMF Out instruction will generate DTMF tones on IO pin 10. So we'll make ours do 4. So let's make another program here. I guess we will try this. And this one will be called Dtmf Out. And we will do DTMF. We'll keep pin 4, DTMF Out. And let's see what the other command line things are. We take the pin, and we have some numbers here. Let's see what they say. On time in milliseconds, I suspect. Yes. So I think it's on time in milliseconds, off time in milliseconds, and then the tones that you would dial. So you can use the default on time, which is a fifth of a second, and the default off time, which is a 20th of a second. And so we don't have to specify those. And the digits, the tone is a variable expression 0 through 15. That's why I said there are 4 rows and 4 columns, which gives you 16 different keys, which is 0 through 15. Well, 12 through 15 are the 4th column tones used by phone test equipment and in ham radio applications. I'm a ham radio operator. Let's try some things out. We will Dtmf Out 4, and we'll put our number up here, and we'll just get rid of this other stuff for now. Maybe I'll add it back in before I post this. So let's see, what do we want to dial? Let's dial something like 4, 1, 3, 7, 5, 5, 7. Is it 755 or no, 782 or something like that? Well, whatever. 7822. I think that's a stick number, but they might not use 755 on the outside number. It might be something else. Who cares? Let's see if we can make this program work. It should dial everything. Then we'll have it, you know what we'll do? We'll have it pause. Let's say have it pause a full second, and then it will loop and do things again. So let's got an error somewhere. Oh, we have to put that stuff in brackets. Where were you guys on that? So let's try it now. Our program is downloaded, and not too bad. I think that would work. I think the phone equipment would work with that. Okay, about enough of that. So you can see that. Well, you know, maybe we'll just do it again. I'm going to stop the scope screen, and let's take a look at what we've got here. I'm going to bring this guy back around to here, like we had him before. Let me set the brightness down a little bit, and we'll just see the same thing going on that we saw before. Let it try to focus on that. And so we've caught it somewhere in the dialing process. But if we spread it out, you can see that they're mixing the various, the two sine waves. when you put them together, they're supposed to, they'll have these funny kind of rounded tooth-like patterns. But those can be made from, just like you can make one sine wave, you can make that waveform from these various pulse widths. And when the voltage gets a little higher, the pulses get far. Oh, what am I doing? I'm sorry. When the voltages get higher, okay, the voltage is going up now. The pulses get fatter. You see the pulses are higher, longer. And I keep going, then it comes down. The pulses are not high for very long, and they're low for longer as the waveform goes down up on this top channel here. We're down at a lower voltage, and the pulses are farther apart, so the waveform is lower, longer. So just think of averaging that lower waveform, and there you go. Here we're going back up again, and we got fatter pulses, and we're going back down a little bit, medium pulses, up to high, back down. So yeah, and down low. So this idea of pulse width modulation, you can actually do, I think we said this before, audio. This is how Class D amplifiers work. And especially the subwoofer amplifiers in cars, they're just, they have tons of MOSFET transistors switching the output on or off in a pulse width modulation or duty cycle controlled way, and then that all feeds a big low pass filter, and then the signal is sent to speakers, and they can, with something that doesn't take up half the car, they can make 800 or 1200 or 1600 watt subwoofer amplifier, or even low frequency amplifier, or even high frequency amplifier, if you just run the pulses fast enough and have fast enough MOSFETs to do the switching. All right, well that's Dtmf Out and Freak Out. So we'll see you next time with another riveting video. And we'll be talking about more things. We're going to do some talking also about analog to digital converters pretty soon. We'll hook one of those up so that we can get a better analog to digital function than if we, measured time as a capacitor discharges or that sort of thing. Well, better, I don't know. If you measure the charge or discharge on a capacitor, if you do it with very good circuitry, you can actually make an excellent, a slow but excellent analog to digital converter. So all that being said, we'll look at an analog to digital converter that does it all in a little chip for us. Sometimes you'll find, and very often nowadays, you'll find that function integrated onto the microcontroller. And some pins, you can turn them on and say, I want this pin to be an analog to digital converter, and inside you'll read a number, but you hook up an analog voltage to that pin, and it will convert that voltage to some number inside. So there we go. I bid you adieu, and we'll see you next time. Take it easy.